What have we got for the results of the drill then? Differentiating 4x cubed. Yeah. 12x squared, take one off the index, multiplying by the old index. Yeah. If we've got a function of x equal to e to the power of x, what's the first differential of that? Yep. If we've got a function 3x squared, what is its value when x is equal to 3? That's what that means. No, this means what is the value of that function when x is 3? Was it 81? No, ain't that big. 27. Did you do it on 4x to the power 3? No. 9 squared. Ah, okay. Right, 10 exclamation mark. What does that mean? So a mathematical meaning. Yeah. Okay, so what was that? Times 10 to the 6, which is, yeah, 3,628,800. But how does it come to that? Any ideas? Well, I'm asking you. I weren't necessarily expecting you to know. Right? What it is what that's called is 10 factorial. And it's a way of expressing 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. All the numbers up to 10 multiplied by each other. Times 12, yeah. You're going to find out. That's a succinct way of writing all that, Jake. Okay? Sorry? Well, if you're doing some calculations and you end and by carrying out that, or you're going to see in a little while, we're going to end up with doing a calculation where we end up with 1 times 2 times 3 times 4, and then we realise we can write that as 4 factorial. Alright, so instead of writing it as a number, we'll write it as 4 factorial, more succinct, and you can kind of see it. You'll end up, what we're going to be doing, there's a pattern to the series, and you can follow it through, that pattern through, once you know what 2 or 3 are, and you can just carry the pattern on. Alright? So that's 10 factorial. What about minus 1 cubed? What's the result of that? Minus 1, yeah. But if you do it incorrectly on your calculator, if you don't put the brackets around it, you can get the wrong answer. Certainly to minus 1 squared you can. Because if you just do that in your calculator, what that'll do is follow the laws of precedence, which is square 1 first and then multiply it by minus 1. That's the wrong answer, isn't it? Yeah? Yes, I think, yes, that's when it's even you'll get a problem. Yeah. Alright, just a little intro drill to what we're going to do in anger this week. Alright? and carry through. Sorry, Jake, go on. Is there an E on there? Oh yeah, sorry, yeah, diverge and converge. I'll put that down here. What does that mean when there's an example of a power series, and that's what we're going to be doing today, looking at power series. Okay, what does it mean, or what are conditions for that power series to diverge? What do we mean by diverge? Sorry? Yeah, I know that's what diverge means, but what does it mean in mathematical terms, do you think? As n tends towards infinity, as n gets bigger, yeah, each term, e.g. x to the n, gets bigger. So if it's divergent, then as we go along all these terms, the value of that term is getting bigger all the time. That's divergent. Consequently, convergent means as n tends towards infinity, each term gets smaller. Okay, and the power series that we're looking at today, one of the conditions for being able to use the power series is that the values converge and not diverge. Alright? So, Taylor and MacLauren series are the topics of your next two lessons. Okay? Taylor and MacLauren series are ways of writing what's called a power series. Examples are quadratic, 3x squared plus 4x plus 2, cubic, 4x cubed minus 2x squared plus x minus 5, and so on. So gradually increasing the powers of x as you go on different functions. If we can express a function as a power series, then it can be written in this kind of form. F of x is equal to a constant term, cu, an x term, an x squared term, an x cubed term. We can carry that on for n number of turns towards infinity. The idea of this is we can represent other functions like an exponential function or a sine function or a cosine function as a power series. And one of the particular advantages of that is that's how computers can do sine, cosine functions, because they can't store a whole table of all the sines and cosines for any angle, so they use a power series to calculate them. And it's again an estimation technique, but to lots of decimal places, and therefore they can do that maths to more powers of n. They can take n a lot further than we can on a piece of paper because we ain't got room. So for instance, your calculator does a square root function, uses the other technique, Newton-Raphson's method, or a method similar to that, estimate that square root to a given number of decimal places, because it doesn't know what the square root of every single number is. So it uses some kind of estimation technique to get it to the number of decimal places that you need it, or will fill your calculator up with decimal places. Okay, so there's some ideas, and that's what this power series is around. So, looking at the next slide, consider the function y is equal to log of x, natural log of x. Right, this is something like I've got something in the wrong order here, I think. Of the Taylor and MacLauren series that we're going to look at is that the function must exist at the point or area of interest. So, looking at the function that I've got graphed on the board there, which is y is equal to ln x, here it looks like it's reached 0 on the x scale, but it hasn't. It never does. It gradually gets closer and closer and closer and closer as we approach 0. But that function does not exist where x is equal to 0. So we can't express that function around the point 0. Okay? So we can only use power series on areas of this function where x is greater than 0. Okay? The significance of that will become clear in a minute. Alright? Generally, if we consider the function at a point A where it exists, okay, then we can say that function can be written as a power series where we've got a constant term, an x term, an x squared term, cubed, all the way up to the power of n term. The key values of all those constants are CO, C1, C2, etc. More about that soon. Further conditions of defining this function as a power series are, and I've already said, that the terms in the series must converge. Also, if the power of series exists, we must be able to find the nth derivative. If we can't do that, we can't do it. It don't work. Okay? Right. If we take that general form, okay, general power series from the previous page, if we let x I equal x, what happens to that function? What do we end up with? We get CO plus C1 What is oh, hang on. Remember, this is times 0 times. I'm just going to write that out again, guys. Because you're not. What you've got to do is say it is. Making A equal to X means we end up with C1 times 0. C2 times 0 squared. C3 times 0 squared. Let green pen go on. The point is, sorry? No, you've got to square, the whole term is squared. It don't really matter where you put it, because if you're multiplying by 0, what does it equal? Nothing. So all these terms equal 0. The only thing left is f of x is equal to CO. Oh, hang on, that's f at I. Remember we made I equal x. So you need to say that it's f at the value of I is equal to CO. Yeah, well, you've made that I and X and on that iteration are the same. Yeah. Okay. This is tricky to follow. I'll grant you that. So we'll take it nice and steady. All right. Now, next step is to differentiate to find f dash of x. So if we differentiate that function, what do we get? Differentiate a constant, what happens? Disappears. Differentiate a constant times x, what are you left with? C1. Differentiate a squared term. Yeah, so we get 2 times C2 x minus a. We're differentiating the function at the top, remember. So that square comes down in front of C2. You get plus 3 C3 squared. That's got to go on the end. X minus a squared. Carry on. Yep. Where are you looking at, Lewis? What's the problem? I've differentiated the constant and end up with nothing. Do you agree? Yeah? Different times x, end up with C1. Do you agree with that? Yeah? Yeah? differentiate C2 times X, I end up with 2 comes down in front, take 1 off the power. Yeah? 3 comes down in front, take 1 off the power. Okay? All alright with that at the moment. Then what we do is we let X equal I again. What does that do? Yeah, it makes C1 therefore C1 is equal to F dash I, and I'm going to put it over 1 shortly. Right, everybody happy with that so far? Differentiate again. F2 dashes X. What happens there? Differentiate C1, disappears. C2, differentiate 3 squared, 6C3, agreed. And the next one would be, I didn't put the next one on there, that would have been 4C4 X minus A to the power of 3. We better include that one. So that become 3 was a 12 C4 X minus A squared. Yep. See that or not? I got that right on that C4 one, and yeah. What's the next step then? X equal I. What happens? These terms disappear. Yep. So we end up with 2C2 is equal to F double dash I C, therefore C2 is equal to actually, looking at my notes, these should be X in here, sorry boys. Yeah, it should be X as well, that one there, sorry. over 1 times 2. How could I better write that? Yeah? Well, I'm going to leave it like that for now then. Going to leave it like that for now. Alright? You'll see why. Oh, hopefully you'll spot it after the next iteration. Alright? So, differentiate again. 3 dashes. X is equal to. Differentiate 2C2, what do we get? Differentiate constant, you don't get anything yet. Differentiate 6C3 X. Yeah. Just 6C3. Now the X goes, doesn't it? And then we differentiate. Minus A, remember. Alright? Let what we left with C3 equal to no, hang on. That's equal to 6, isn't it? But how else can we write that? Yeah. So we can write that as 1, 2 times 3. 1 times 2. How else today? We can write 1 times 2 times 3. Yeah, but look at, you're still dividing by 6. 1 times 2 is 2, times 3 is 6. Why do it? If you look at it, and if we carried on, if you look at this one, how could we write that? We could 2 factorial, right? 1 times 2, 2. Yeah. If we differentiate again now, what do you think we end up with? C4. Well, that's going to equal x over 4 factorial. Yeah? Carry it on again. C5 is equal to F5 x over 5 factorial. As an infinite power series. So we're looking for the pattern. That just so happens you add 1 to just a clear way of showing that. If you had 2, what was it? 3 factorial is 6. 2, 6, 24. What's 5 factorial? Use the pattern then, would you? Is the pattern so obvious? There's 1 factorial, 2 factorial, 3 factorial, and so on. You're just doing it so that you can get rid of 4 terms apart from the constant term at the start. I mean the final. Which final one? No, but what you remember is technically that's a power series moving towards n being at infinity, so it goes on forever, Dom. Yes, you carry on if you add more terms. See later with a MacLauren series. Shape of the you could be given a power series question in the exam, which you'll see something along the lines of what I might ask you to do next week. Yeah. But to find X number of terms of a particular function. Yeah, that once you can do it, yeah. But what I'm trying to do here at the moment is show where the MacLauren series done that, then we'll just use the MacLauren series formula to model some functions that we know the shape of anyway. Alright? So to sum that up, what we can now do is replace the constant terms in the original formula with what we've found. We end up with this. F of x is equal to C1 is f at a. We wrote that, I hope. Yeah. C0, sorry, is FA. Big long F dash one factorial x minus a squared over 2 factorial plus third derivative of the function of a 3 factorial, the nth derivative and that should be cubed in there, x minus a over n factorial. That's the power series for a particular function f, focusing on the point A, where A is the value of x at that particular point. Okay, so we might, you'll see what I mean by focusing on a point a bit later on. Become much clearer. Alright, can I change on to the next slide? Undone, yeah? Right, taking that pattern from the previous page, so I've typed it out there, up to the third term, we could formally define that much shorter by saying f of x is the sum of between 0 and infinity of f to the n, x minus a to the n over n factorial. Yeah, and that function formula is called the Taylor series. Furthermore, if this function exists at the point where x is equal to 0, we can simplify that formula to f of x is the sum of all between 0 and infinity of f to the n times 0 x to the n over n factorial. That is the MacLauren series. This is not times 0, sorry, it's value of f to the n when x is 0, when the function equals 0, x is 0, sorry. That's a modified Taylor series called the MacLauren series. But MacLauren series only works if the function exists at 0, where x is equal to 0. You can't use it if the function doesn't exist. So MacLauren series would not work on that y is equal to ln x function. Okay? It'll only work if the function exists, if it's got a value that doesn't give you an error on your calculator when you allow x to equal 0. Yeah, well, it only... you have to get a valid result. Put in ln 0 in your calculator. Math error. Yeah, because that function doesn't exist where x is equal to 0. In fact, if x is equal to 0 or less than 0, it doesn't exist. MacLauren series will only work if you put x is equal to 0 in that function. Do you get a valid result? A sine function you would, wouldn't you? You'd get 0. Yeah? Cosine function you'd get 0. For instance. So you can use a MacLauren series on them. Alright? Where it doesn't exist at 0, as you'll see next week, we need to use the Taylor series. So we can focus on a different point A. For instance, we might decide to focus where I is equal to 2. The MacLauren series can't be used on that. We would have to use the Taylor series and choose a value for A higher than 0. Yep. Right, let's have a look at an example of using the series. Okay, so what we're going to do is determine the terms up to x to the power of 6. Okay, for cos fx is equal to cosine of x. So that's our function we're going to look at. So what does f at 0 equal? 0, 1. Yep. Next step, differentiate the function. Differentiate cosine of x. And we're looking at this, well, all the time when x is equal to 0, by the way. We're using the MacLauren series. So what's the differential of cosine of x? Minus sine x. F double dash at 0 is equal to, so, yes, sorry, double dash. So sine of 0 is so therefore minus the sine of 0 is 0. Yep. F double dash of x, so we got to differentiate the function minus sine x. Minus cos x. The value of that at 0 is minus 1. F triple dash fourth differential yep. See what I mean about patterns emerging? Yeah, so if we carry that on, we go 0, minus 1, 0, 1, and that carries on. Let's carry on. If we substitute that into a MacLauren series, like so, we end up with C1, C0 is 1, when you run out of space on these boards. Right, let's go over here. Plus x cubed over 3 factorial times 0 plus x to the 5 over 5 factorial, 4 factorial, sorry, x to the 4 over 4 factorial times 0 times 1, that's right in a minute, plus x to the 5 over 5 factorial times 0 plus where we could carry that on. Yep, so these are the constants that we've found in each there. So we've gone 1, 0, minus 1, none, 1, followed that pattern. So 1, 0, draw under that if anyone wants, 1, 0, minus 1, 0, 1, 0, minus 1. And then what we can do is simplify that to cos of x is equal to 1. This term is multiplied by 0, so it doesn't exist. Are we looking, boys? This is multiplied by 0, so we don't need it. This one is multiplied by minus 1, so that's minus x squared over 2 factorial. The next term is multiplied by 0, so it disappears. This is multiplied by plus 1, so it's plus x to the 4 over 4 factorial. Our 5 term is multiplied by 0, so it disappears. This is multiplied by minus 1, so it's minus x to the 6 over 6 factorial. And we can carry that on. And the question asked for 4 terms. Yeah. The question asked for 4 terms, but we've gone up to x to the power of 6 because the odd terms are missing. Yeah. So when you model a cosine function using MacLauren series, you only get odd terms of n. Right, let's just take a look at that. Looks like. So if we graph the y as cos x function, we get that. If we go up to the third term with the power series, so the blue graph the power series up to the third term, x to the 4 over 4 factorial. We are, the blue function is close to the red one, around, we're focusing around this area here where x is equal to 0. And then if we add another two terms, function becomes even closer to that. And if we carried on adding terms, we went to the nth term being infinity, we would have exactly the function cos x. Okay? To when x is 0, sine of nothing, zero. Yeah. First differential sine x is cos x. Value of that when x is 0 is 1. Differential of cos x is minus sine x. Value of that at x equals 0 is nothing. Third differential minus cos x. Value minus 1. Value of that one is nothing. You're inside, aren't you? Alright, so the pattern starts with 0, but still goes none, 1, none, minus 1, none, 1. Spell it wrong, Jake, alright? You'll not make that again, hopefully. So, therefore, we can write sine x as no constant term. That first term, constant term, is like y-axis shift sine function 0 when x is 0. Therefore, there should be no term. We haven't got one. So what was the first term in the power series? Yeah, x. Yeah. Yeah, I'll write out the plus x to the 5 minus 7 factorial. And so the pattern is and if we was to put that in the graphing software, turn these ones off, y equals sine x y is equal to x minus plus minus x cubed x to the power 3 over 3 factorial plus x to the power 5 over 5 factorial. And again, as I add terms, you can see it's getting closer and closer to the function in this area around x is equal to 0, because the MacLauren series focuses on that area. Minus x to the power of 7 over 7 factorial. Plus x to the power of 9 over 9 factorial. Yeah, we're going to look at one now where other constants come into that, in front of those extra power terms. Alright, so have a look at the next one on the next page. It's got time to start having a look at that one, and you can carry it on after. Using the MacLauren series, find the first 5 terms for the expansion of the function e to the power 3x. One, 3, 9, 27, 81. Yeah, because it is e to the 3x. Yeah. Nine e to the 3x, 27 e to the 3x, and so on. Yep, given a power series, e to the 3x being equal to 1 plus 3x plus 9x squared over 2 factorial plus 27x cubed over 3 factorial plus 81 x to the 4 over 4 factorial, and so on. What's the pattern for the constants there? Are all multiplied to the previous. Right? If we look at the function graphed, there's the actual function graphed, e to the 3x. 3 terms, power series. Remember, the focus is going to be around the value where x is equal to 0. And if I add more terms, I get closer and closer to that function. Right? So, heavy stuff to start with this week, but the actual maths behind it and using the MacLauren series with a reasonably simple function to differentiate, not too bad. Alright? And like I said, in the exam, if we just look at the sine function again, and its series, if we look at this function here, the 2 of them, around this area where it's equal to 0, if we integrate either the MacLauren series function, this one, or we integrate the sine x, we're going to get very close results, aren't we? Because if we integrate between plus pi and minus pi, we're going to get a fairly close estimate of integration, whether we use the actual function or whether we use the power series. Therefore, more complex functions that might be difficult to integrate but easily differentiate you would then power series and integrate the power series. Yeah, we have not already integrated simple power terms. Yeah, you could, if we took those first three terms there, Dom, could you integrate 5 and find the... We've already done that, haven't we? Could you integrate each you can, yeah. 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 Okay.